Swayam Prabha. Digital India. Educated India.
Welcome to the first lesson of the 9th module, which is on stability of columns part 1. In fact, in the previous modules we have discussed certain aspects of the stresses in members, and consequently we have looked into the effect of bending in a member, where we have evaluated the deflection of the member. Now, in this particular lesson we are going to discuss a different aspect, which is a stability of a member, which we designate as column. Now, it is expected that once this particular lesson is completed, one should be able to understand the concept of buckling of column members. In fact, we will define what we mean by column member, which member we term as column, and then we will look into certain characteristic features which we call as buckling. So, buckling of column members under axial compressive load, and one should be in a position to evaluate critical buckling load in column members of different types. Now, we will look into that what we really mean by critical buckling load, that the member which is subjected to axial compressive load, in which load is going to buckle or deform. The scope of this particular lesson therefore includes the recapitulation of previous lesson. In fact, the last module we have looked into the aspects of the combined stresses. We will look into the certain aspects of the combined stresses while answering the questions related to that, and this particular lesson includes the concept of stability of column members, evaluation of critical buckling load in different types of column members. Now, the different types of column members we mean, we look into that what are the different types of supports the column members have, and what are the contribution of the axial load in buckling of those members. And then we will look into some examples for the evaluation of buckling loads in columns. Well, now let us look into the questions which were given in the last lesson. The first question was that how will you evaluate the combined stresses if the member is subjected to axial load and torsion simultaneously. Now, as I said that the previous lesson we had discussed about the concept of the combined stresses, and you had seen that if a particular member is subjected to an axial pull P along with a twisting moment T, then what will be the effect of this combined loading in the member. Now, as you know that the axial load which is acting in the member, which is concentric, that means acting through the center of gravity of the member, will contribute to the normal stress sigma, which is equals to P divided by the cross sectional area. So, everywhere wherever you take the element on the surface, you will get, or in interior at any point, the normal stress will be equals to P divided by A, and the contribution of the twisting moment T will be in the form of shearing stress, as we have seen while discussing the effect of the torsion on member. So, thereby if we take an element, this will be subjected to the normal stress sigma and the shearing stress tau, and as you know that if a particular element is subjected to the combined action of the normal stress and the shearing stress, we can plot these stresses in the Mohr circle in terms of sigma and tau, and then we can compute the value of the maximum normal stress, which we call as sigma 1, and the minimum normal stress, which we call as sigma 2. We call these also as principal stresses, and the maximum value of the shearing stress, which we call as tau max. So, these stresses we can evaluate when they are subjected to the combined action of the axial load and the torsion. So, when a member is subjected to the axial pull or axial compressive force and a twisting moment, the resulting stresses are the normal stress and the shearing stress. Shearing stress comes from the twisting action, and then when normal stress and shearing stress act simultaneously, we can compute the values of the maximum tensile or compressive stresses and the maximum value of the shearing stresses in the member. Now, the second question posed was, how will you evaluate the principal stresses if a pressure vessel is supported on two supports at a distance apart? Now, as you had seen that a pressure vessel, when it is subjected to some liquid which is exerting pressure on the container, we get two types of stresses which we call as sigma c, the circumferential stress or the hoop stress, which is given by sigma c equals to P r by T. Consequently, we get the longitudinal stress which we call as sigma L, which is equals to P r by 2 T, where P is the internal pressure, R is the radius, the outer radius of the cylindrical vessel, and T is the thickness of the vessel. So, these are the stresses, the sigma c and sigma L, the circumferential stress and the longitudinal stress that we get on the surface. Now, when this particular vessel is supported on two supports, thereby if we take the weight of this container along with the contained liquid, we can idealize that particular form in this particular form, where we have two supports with a load which is distributed over the entire length of the vessel. The entire length of the vessel we can consider as a beam member, which is subjected to its own weight along with the contained liquid and supported at these 2 points, let us call they as A and B. Now, as you know, this particular beam member, when it is subjected to a load of Q uniformly distributed, we will get a moment diagram which will look like this. Now, because of this bending, there will be bending stresses, and as you know, the bending stress introduces the normal stress which is m y by I, and this depending on the position of the element, it could be compressive or tensile when you are talking about with reference to the neutral axis. So, thereby that will contribute to the normal stress. Now, this stress, the normal stress due to bending, will get added or subtracted from the longitudinal or the normal stress we get from the pressure vessel, and they are shown over here. Now, P r by 2 T is the contribution from the pressure vessel and m y by I is the contribution from the bending. So, these will give us the resulting normal stress and in the x direction, and this will give the normal stress in the y direction. Now, in this particular problem, of course, we have not considered the effect of the shearing stress. However, if we compute the value of the shear, there will be effect of the shearing stress as well, but in the if we do not consider the shearing effect, then this element will be subjected to the normal stress sigma x and sigma y, and from this again sigma x and sigma y, since there are no shearing stresses on this element, these are the principal stresses or the maximum value of the stresses, the maximum tensile stresses that will be occurring in the x and y direction, and you know, at any direction we can compute the stress based on these stresses. Well, the third question was that on a road sign which we normally use, what kind of stresses this will induce, the wind load will induce in the vertical member. Now, as you have seen that the road sign which is projecting from a vertical shaft is subjected to the normal, when the wind acts normal to this particular plate, it will be subjected to the wind force which will be acting through the center of gravity of this particular plate. And if we call this load as P, this load if we transfer to the vertical shaft member, it will be transmitted with a twisting moment T. So, if we idealize this particular member in this form, like you have a beam which is subjected to a lateral load P and a twisting moment T. Now, this lateral load P will produce a maximum bending moment at the support, which is equals to, if we call this distance as A, P times A is the bending moment over here, and this P A moment will introduce the normal stress sigma, which is equals to m y by I. Also, at this section there will be shearing stress because of the shear force due to load P, and that is equals to tau as equals to V q by I b. and the twisting moment T will have the stress here, will produce shearing stress, which is tau, which is equals to as you know that T by J is equals to tau by rho. So, this is T rho by J. So, the total effect of the shearing stress you will have from the twisting moment as well as from the shearing force, and there will be normal stress because of the bending. So, the member, vertical member, which is subjected to wind load, the road sign which is subjected to the wind load will have the combined effect of the bending stress, the shearing stress and the shearing stress from the twisting moment. And once we know the normal stress and the shearing stress, then we can compute the value of the maximum value of the normal stresses or maximum principal stresses. If we plot them in a Mohr circle, we can compute the value of sigma 1 and sigma 2, which are the maximum normal stresses, and thereby they are the principal stresses. Well, before we go into the stability aspects, let me discuss the problem which I had assigned to you last time, and this is related to the combined effect of the bending and the twisting moment in a member. A steel shaft of diameter d, which is unknown, is subjected to a bending moment of 1.2 kilonewton meter and a torsion of 0.3 kilonewton meter. Now, if the allowable tensile and shear stresses are 80 megapascal and 40 megapascal respectively, we will have to determine the diameter d of the shaft. So, this is a situation where the shaft is subjected to the combined action of bending moment and the twisting moment. Now, when the member is subjected to the combined action of bending moment and twisting moment, then we get the stresses in this form. Say for example, if we have the shaft of diameter d, then as we know the sigma is equals to m y by I, and y here is the maximum distance from the neutral axis, which is d by 2. So, this is equals to m times d by 2 and I is pi d 4 by 64. So, this if you compute it, it comes as 32 m by pi d cube, and this is what is indicated over here, that sigma x, the normal stress which is arising due to bending, is equals to 32 m by pi d cube. And here all the parameters are known because bending moment is given as 1.2 kilonewton meter, which is into 10 to the power 6 Newton millimeter, and d is the parameter which we will have to define, and if we compute this comes as 38.4 into 10 to the power 6 by pi d cube. Now, consequently, when we have the twisting moment, that will introduce the shearing stress, and again as you know that the value of the shearing stress will be equals to T rho by J, and that is if we can compute tau is equals to T rho by J. You know rho is the maximum distance from the center, which is d by 2 again. So, T d by 2 and J is the polar moment of inertia, which is pi d cube by 32. So, pi d 4 by 32. So, then it becomes as equals to 16 T by pi d cube. So, this is the shearing stress which is getting generated because of the twisting moment T. Now, here also except d, all other parameters are known. The twisting moment is 0.3 kilonewton meter, and thereby tau x y comes as 4.8 into 10 to the power 6 divided by pi d cube. Now, when you have this normal stress sigma x and tau x y, we can compute the value of the maximum tensile stress sigma 1 either using Mohr circle or using the transformation equation, and which is sigma 1 equals to sigma x plus sigma y by 2. Now, here sigma y being 0, so this is sigma x by 2, and since it is maximum tensile stress, that is why we have taken the sign plus, equals to root the radius, which is sigma x minus sigma y by 2 square plus tau x y square, and sigma y being 0 again, this is sigma x by 2 square plus tau x y square. Now, if we substitute the values of sigma x and tau x y in this expression, sigma x by 2 is 19.2, and this is of course 10 to the power 6 divided by pi d cube has been taken out, and this is root of 19.2 square plus 4.8 square, which is tau x y, and this gives us a value of d. If we compute from this expression, we get 53.7 millimeter. Now, this is the value of the diameter of the shaft, which is corresponding to the maximum tensile stress of sigma 1, which is equals to 80 megapascal. Now, if we have to satisfy the criteria of the maximum shearing stress, which is equals to 40 megapascal, and as you know the maximum shearing stress is nothing but equals to the radius of the Mohr circle, which is this, and that is sigma x by 2 square plus tau x y square, and if we substitute that, this is 10 to the power 6 by pi d cube taken out, we have root of 19.2 square plus 4.8 square, and this gives us a value of 19.8 into 10 to the power 6 by pi d cube, and as you know the limiting shearing stress is 40, from this we get a value of d as 54 millimeter. Now, as you can see that we have computed the value of the diameter from the maximum tensile stress, also we have computed from the criteria of maximum shearing stress, and since both the criteria has to be satisfied, because you cannot provide a diameter which will satisfy one and it will not satisfy the other, then naturally it will not stand, it will fail. So, you will have to provide the maximum value of the diameter corresponding to the two satisfying both the stress criteria, and thereby the diameter of the shaft comes as 54 millimeter. So, the shaft diameter has to be 54 millimeter, so that both normal stress and shear stress criteria are satisfied. So, this was the solution for the example which we had given last time. Now, having discussed about this effect of these combined stresses, now let us look into that stability aspects of the column. Now, before you really go into the stability part, let us look into these two aspects. As you remember that in the first module we had discussed that we are concerned about the 3 S's in the strength of materials. One we call as the strength, and in the strength, as you have seen that we have computed the value of the stresses. Say for example, if you have an axial load divided by the cross sectional area gives you the normal stress. Now, also we have computed the shearing stress for the from the twisting moment, or we have computed the normal stress from the bending moment. Now, these stresses, as we have seen, must withstand the stresses that can be withstood by any of the material that we are providing for constructing any of these elements. Now, naturally that says that the strength of that particular material is such that it can withstand these stresses, and that is what we have designated as the strength criteria for a particular member. Consequently, we have looked into that if you have a member which is subjected to load, it will be undergoing deformation. Let us take for example that when you have a member subjected to the axial load P, we had corresponding deformation delta which was equals to PL by AE. Now, if we like to relate the delta with P, we can write this as P as equals to AE by L times delta. Now, here if we define like this, that if we like to have unit deformation, the load which we need is corresponding to this particular term AE by L, and this is what we call as the stiffness of the element. That means, this is the axial stiffness of the member which will need this much of load P to produce unit displacement delta or unit deformation delta. Consequently, say for example, in a particular beam, simply supported beam subjected to uniformly distributed load, we had seen that delta is equals to PL cube by 48 EI. Now, here also if I like to write P in terms of delta, we can write P as equals to 48 EI over L cube times delta. Now, if we like to have unit deformation or deflection, the corresponding load which we need is equals to this amount, which we term as the stiffness of the member. Or if we are talking about the say the twisting moment, as we know that tau is equals to T rho by J, and this will again is equals to G theta. I mean T by J is equals to G T by tau by rho is equals to G theta by L. So, T is equals to G J L by times theta. Here also if we like to have unit rotation, the corresponding twisting moment that we need is equals to G J by L, and that is what is twisting stiffness. Now, you see in each of these cases, as we are looking into that, we need the stiffness of the member whether in terms of AE by L or EI by L cube or GJ by L. They are the characteristics of the member concerned, where the cross sectional area or the moment of inertia or the polar moment of inertia are introduced or are connected with. Now, so these are the parameters which we call as the stiffness. So, these are the two aspects, the strength and stiffness parameter we have already looked into. Now, thirdly, the aspect which we are going to look into is the stability of a member. Now, in this particular lesson, of course, we will be discussing about the stability with reference to the column member, though strictly speaking stability does not mean the stability of column alone, it can be stability of different members as well. But in this particular lesson we will be looking into, or in this particular course rather, we will be looking into the stability of the column members only. Now, a column member is a member which generally carries an axial compressive load, and we call those kind of members as the column members. Now, let us really look into that what we mean by the stability of columns. Now, columns we can categorize into three groups. One we call as short columns, where the axial load is applied to a member in such a way that everywhere we get the stress, as you have seen that sigma will be equals to P divided by A, the normal stress, and this member, if we keep on applying this load P, will fail by crushing or yielding of the material when the stress will go beyond the permissible value of the material. Another category we call as a long column, where the member fails by buckling. Now, let us look into this aspect from these two this very small experiment. Now, here I am considering two members, the cross section of which is a rectangular one, and they are of the same cross section. If you look into these two members, I have one member which is a shorter length and I have another member which is a little longer length, and the cross section of these two members are the same, they are rectangular in nature. If you look into the cross section, they are identical. Now, when I am talking about this shorter length member, if I am applying the axial load, we will find that the stress at any level will be P divided by the load applied divided by the cross sectional area. Now, if I take the longer member and if I try to apply the load, we will find that this particular member is going to bend in a form, and this is what we call as buckling. Now, this particular member, as you can see that we are applying the axial load and it has taken a bend shape, and thereby it has undergone some amount of bending, and this is what we call as buckling. So, in case of the shorter member, the stress which we had obtained, they are by the crushing of the member, or the stress level at any point goes beyond the permissible value of the material stress. In case of the long columns, or in case of the member which is a slender one, when we apply the load P, if we increase this load gradually, as we have observed that it takes this particular bend shape, and this is what we call as buckling. Now, in this particular shape which is little unstable, if we try to apply a lateral load, there will be deformation, and this deformation will be in an unrestrained manner, and that is what we call as the buckling. The deformation of the member in an unrestrained manner causes the failure of the member, and we get intermediate columns which can fail by the combination of the crushing and buckling. Now, for this it is very difficult to arrive at the theoretical basis. So, we resort to some experimental or empirical formulae for evaluating the critical load for the intermediate columns. Now, if we try to look into the animation part of it, that if you have the member when they are subjected to load, as you can see is in a straight form, or when the first load is added, as you can observe is in a straight form. You see, now it is still straight. Now, we have added load, it is deformed slightly. Now, if when you add load further, it goes in an unrestrained manner. Now, let us discuss this stability aspects of column through a model which we call as a buckling model. Now, in this buckling model, we consider two rigid bars AB and BC, and they are connected by a pin at point B, and at point B we add a rotational spring having a stiffness beta. Now, when this particular member A, B and B, C, they are concentric, they are subjected to a load P, it will be in a stable form. Now, if we add a little disturbance to the member, then the point P will move. So that the deformation which we get, the member will undergo a rotation called theta, which we presume as a small deformation. Now, when this particular member point B moves, then the rotational spring which we have at point B will have some amount of moment generated, which will try to bring this member back once we remove the disturbance. That means, this particular moment, which will be equivalent to the stiffness times the total rotation that these two members undergo, which is equals to 2 theta. So, the restoring moment for the spring M is equals to beta times twice theta. Now, this particular restoring moment will try to bring these two members in their straight form. Now, if the on the other hand, what happens is this particular load P will try to increase this deformation at point B. That means, there will be it will try to increase this rotation theta. Now, as you can see that the effect of the axial load which is trying to deform the member or buckle the member is against or opposite to the restoring moment that is being exerted by the rotational spring at point B. Now, this particular model you can compare that with the previous example, as I was showing you, that you have a long member subjected to axial load. Now, there the bending or the buckling is over the entire length of the member. Now, here that elasticity is introduced through the rotational spring only. Now, in this particular state, if we remove the disturbance, it will come back to its original position. Now, if we go to the particular load when, so that particular configuration when after removal of the disturbance it comes back to its original position, we call that particular state as a stable state. Now, in that undisturbed state again, if we keep on increasing this load P, a situation will come when the deformation will be large and thereby there will be the member is going to collapse, when the restoring moment will not be able to withstand the effect of the compressive load, or thereby the load P which will be applied will be greater than the restoring moment that is being offered by the rotational spring, and that particular state we call as unstable state. Now, so you see that one state we get as a stable state and another state we get as unstable state corresponding to two values of the axial compressive force P. Now, in between these two states, between the stable state and unstable state, we get an exclusive value of P, which is the in fact the boundary between the stable and the unstable state, and that load we call as the critical load. And that at that particular load, if the member is subjected to in a stable equilibrium position, a little disturbance in that member can cause the failure of the member, and that is why we call that particular load as the critical buckling load. Now, if we like to analyze that what will be the critical buckling load for this particular model, we take the free body diagram of this whole thing, the whole member, and if you see that this horizontal force, if we call this as H, and if we take the moment of all the forces with respect to A, we see that H is going to be equals to 0. Now, if we take the free body of the top part of the member, the part BC, which is like this, where you have the small deformation theta here, the axial force P is acting and the restoring moment M and the resistive force P, the reactive force P is acting at point B. Now, as we have seen that M is equals to beta times twice theta is the restoring moment, as we have called it, that when it is trying to restore its original position. If P is small, if restoring moment is larger than the P, it will come back to its original position and thereby the column is a stable member if the disturbance is removed. But if this restoring moment becomes smaller than the P or P becomes larger than this restoring moment, the member is going to collapse. And so, at the point when we are calling that P is in the boundary between the stable and the unstable state, that means at that particular point of time the load is just equal to the restoring moment. So, when axial compressive load P is equal to the restoring moment in this particular model, then it will be in a just state of equilibrium, and any additional load will cause the instability of the member, or the member is going to collapse due to the unstable situation. So, if we equate that if we take the moment of all these with respect to B, and m minus P times, now this is theta and this length is L by 2. So, this distance is L by 2 times theta. So, P times L theta by 2 minus A, or m minus P L theta by 2 equals to 0. Now, this gives you m as equals to 2 beta theta. So, 2 beta minus P L by 2 times theta is equals to 0. Now, here if you see that if either theta could be equals to 0 or this bracketed term equals to 0. Now, if theta is equals to 0, then naturally this is in a straight form. So, there is no buckling. Now, hence this bracketed term is equals to 0. If we set that gives us a value of P equals to 4 beta by L, and this is what we are calling as the critical load. And you see this critical load is independent of theta. That indicates that whatever may be the value of the theta, the critical load P is equals to the 4 by L times that stiffness, the stiffness of the rotational spring, which is analogous to the stiffness of the model which we are looking into, the long member which we are looking into. Hence, the critical load is equals to 4 beta by L. Now, what does we mean by this particular critical load? This is the boundary between the stable and the unstable situation. If we have load less than P critical, that means the member is in a stable form. That means, once we remove this disturbance, it will come to a perfect state, the perfectly vertical state. And if it is in a such a state, if we add disturbance if it is in the critical load, if we add any disturbance to it, it is going to cause the collapse, or the member will become unstable. Now, so what we need to look into is that the different state which we can compare with this particular situation, that if a ball, if it is placed in a member which is upwardly concave, here wherever is the position of this particular ball, it will come back to its lowest position, and thereby this is a stable form, and that you can plot it with respect to load versus theta. If we say this is as theta, that means in a stable form, once you deform it, if you add some disturbance to the member and bring it back, it will always it will come back to the perfectly vertical position, and this is a stable state. Now, this is a state which is unstable. That means, at this particular point, though at this particular point it is stable, but a little disturbance to this can cause the failure of this particular form, this will move. That means, at this particular state, at a particular state when load has gone to the criticality, the member can be just vertical, that means the theta could be equals to 0. So, it is just in a critical state. If we give a little disturbance this way or that way, that can cause the collapse of the whole member, and that is what we call as the unstable state, and this is what is being represented through this particular diagram. Here P is greater than the P critical, and this particular point. So, this is the unstable state and this is the stable state, and this particular one is the neutral state. Now, here wherever you place this position, it will always remain in that particular position, and that is what we call as the just equals to the critical load. This is we call as a neutral position. Now, we can look into this particular form where you see that once we remove this, it comes back to its original position, because the restoring moment is more than the axial force, and that is why the restoring moment is putting it back in its original position. But if the load becomes larger, you see that it collapses. That means, if the axial force becomes higher, then the member collapses. Well, then we come back to our original discussion again after looking into the aspects of the model which we have looked into the buckling model. Now, we are interested to evaluate that what will be the critical buckling load for a member, and for that we start with a situation that we have a column member which is pinned at both ends, and this is an idealized form of the column where the axial load P is acting perfectly concentric with respect to this member. Now, here we choose the axis system in such a way that x goes along the member length and y is perpendicular to this. That means, if we rotate by 90 degree, we get the situation that x is in the positive x direction and y is in the positive y direction, as we have assumed for a beam member. Now, the length of the member is L. Now, as we have seen that at the criticality, when we reach to the P critical, the slightly bent form of this member, if we call this as theta, the member can be in the equilibrium state, beyond which if we add to this particular state, if we add any disturbance, then it is going to cause a failure of the member, and we are interested to evaluate this critical load corresponding to which it will be in a state of equilibrium. Now, if we take a section at a distance of x from end A from 0 point, then the free body diagram of this particular part of the deformed state of the member is this, where this distance is equals to y at a distance of x, and at this point you have the reactive force P and the moment M. Now, if we take the moment of all the forces with respect to say at this point, if we call this as D, then moment M plus P times y is equals to 0, or M is equals to minus P into y. Now, as we had seen that the flexural equation or the differential equation for evaluating the deflection of a member on a beam member was E I d2y dx2, which was equals to M, and M, the bending moment here, is equals to minus P y. Now, based on these particular aspects, we would like to derive the critical load for this particular member, and this derivation was presented by the great Swiss mathematician Leonhard Euler in the year 1744, wherein he had given this particular derivation, based on which we compute the value of the critical load P critical, and thereby we generally designate this critical load as the Euler's critical buckling load of a column member, or it is a Euler's critical buckling load formula. The expression which we get for evaluating the critical load, we call that as the Euler's critical buckling load formula. Now, let us see how do we get this value of the critical load corresponding to this. Now, as you have seen now, E I d2y dx2 is equals to the moment, which is equals to minus P times y. Now, if we take this on the other side, we have E I d2y dx2 plus P into y is equals to 0. Now, if we divide the whole equation by E I, we have d2y dx2 plus P by E I times y is equals to 0. Now, we designate P by E I term as equals to lambda square. So, P by E I is equals to lambda square. So, this is d2y dx2 plus lambda square y is equals to 0. Now, if we choose a solution of this y as equals to e to the power m x, then we get an expression that m square plus lambda square into e to the power m x, this is equals to 0. Now, since e to the power m x equals to 0 will give y equals to 0, which is meaningless. So, m square plus lambda square equals to 0, and thereby m is equals to plus minus I lambda. Now, corresponding to this solution, we have the solution y as equals to C1 sin lambda x plus C2 cos lambda x, where C1 and C2 are the unknown constants. Now, the boundary conditions which we have for this particular member, at this member is pinned at both ends. So, it is hinged at both ends. So, at x equals to 0, the deflection y is equals to 0 of this particular point, and that gives us that value of C2 is equals to 0. and also at x equals to L the deflection is 0, the deformation is 0 over here. So, at x equals to L if we substitute y equals to 0, we get C1 sin lambda L is equals to 0. Now, from this particular expression, as you can see that either C1 can be 0. Now, if C1 is equals to 0, that means y equals to 0, that means there is no deformation in the member. But since C1 cannot be 0 will lead us to a solution that which does not mean the buckling or the deformation of the member, then sin lambda L has to be equals to 0. Now, if sin lambda L equals to 0, it gives that lambda L in a general form is equals to n times pi. So, that means for different values of pi, pi to twice pi, thrice pi, the value of sin lambda L will be equals to 0. Now, if we square this up, we get lambda square is equals to n square pi square by L square, and lambda square as you know is equals to p by E I. So, p by E I is equals to n square pi square by L square, and therefore, p is equals to n square pi square E I over L square. So, we get then p is equals to n square pi square E I over L square. Now, here the minimum value of n can have values 1, 2, 3. Now, minimum value of n will lead to the critical load for this particular member, and if we substitute n or we take n as equals to 1, then the critical load for this becomes pi square E I by L square. So, if we have load less than pi square E I by L square in a column which is hinged at both ends, then it will be in a stable form, and if we go beyond that load, then that particular member is going to collapse or fail in buckling. Maybe the stress level could be lower than the yield stress, the P by A if you compute that could be less than the yield stress, but the member will fail in excessive deformation which we call as buckling. Now, this is what is indicated over here. The critical load PCR is equals to pi square E I over L square, and this is what we call as Euler's critical buckling load formula or Euler's critical load. P critical is as Euler's critical load, and consequently as we have seen that C1 y is equals to C1 sin lambda x. For lambda if we substitute pi L or in a general form as n pi L, this will give you n pi x by L as the equation of the elastic curve. Now, since C1 is not determined uniquely, so naturally the value of the deformation which we get is not uniquely defined, and so we can have an arbitrary value or arbitrary shape of the particular deformation, and this is what is the deformation shown over here. You see when n is equals to 1, this is the way the member is going to deform, and you have the corresponding load as the critical load. Now, when n is equals to 2, we are going to have the critical load as 4 times P critical, and since it is larger than this critical load, naturally at this point you will have to have some kind of a support, so that you get the deformation in this particular pattern. When n is equals to 3, then the load it can go up to 9 times P critical corresponding to this one, and thereby at the third point you need to have some kind of a support, and thereby the column can take a shape of this particular form. Now, these are the shapes which we generally call as mode shapes. Now, let us look into the critical load corresponding to a column member where the supports are of different type. Here one end is fixed and the other end is free. In the previous case we had a member where both ends were pinned or hinged. Now, here one end is fixed and the other end is free. Now, if that happens at the critical state, it may deform in this particular configuration, and beyond which if we add disturbance to this particular member, this is going to cause the collapse of the member, and thereby corresponding to this state we call the load as the critical load. Now, again if we take a free body of diagram of this particular part which is at a distance of x from the origin, which is let us call as A, then this is the free body diagram. Now, at this particular point this distance from here is equals to y, and thereby and at the top we have taken the maximum deformation of the member with respect to its original position as delta. So, thereby this particular length is going to be equals to delta minus y. So, if we take the moment of all the forces with respect to this particular point, then we have moment m minus p times delta minus y equals to 0, and this is equals to the value of the moment. Now, if we substitute the value of the moment in this equation, differential equation for the elastic curve, which is E I d2y dx2 is equals to p times delta minus y, this will give us the d2y dx2 plus py is equals to p delta. We will have E I d2y dx2 plus py is equals to p delta. Now, if you divide this by E I, you will have d2y dx2 plus lambda square y, because p by E I you have called as lambda square equals to lambda square delta. Now, it will have two solutions. One is the complementary solution considering this as 0, and then corresponding to this we will have the particular solution. Now, when this is equals to 0, as we have seen that the solution is equals to C1 sin lambda x plus C2 cos lambda x. Now, when you have the right hand side part, we can evaluate the particular solution. If we assume say solution y as equals to a x square plus b x plus c in this form, then we will have d2y dx2 as equals to twice a, and thereby if we substitute in that, we have twice a plus lambda square y, which is a x square plus b x plus c. This is equals to lambda square delta. Now, if you take the coefficients of x square x on either side, since on right hand side we do not have any term on x square and x. So, thereby we will have a as equals to 0 and b also as equals to 0. Now, consequently, we will have that lambda square c is equals to lambda square delta, and thereby c is equals to delta is the solution. So, we will have y is equals to delta is the particular solution for this particular case, and thereby we will have the solution in this form, that y is equals to C1 sin lambda x and C2 cos lambda x plus delta. Now, we will have to solve this C1 and C2 from the boundary condition, and as you can see at x equal to 0, y is 0 here, and x equal to 0, y dy dx also is 0, the slope is 0 here, and also at x equals to we will have to satisfy x equals to L, the y is equals to delta. Now, if we satisfy this, now what we get is this, that at x equal to 0, y equal to 0 will lead you C2 is equals to minus lambda, and at x equal to 0, dy dx equals to 0 will lead us C1 is equals to 0, and thereby we get y as equals to delta into 1 minus cos lambda x, and we will have to satisfy that at x equals to L, y is equals to delta, and thereby we get that delta is equals to delta into 1 minus cos lambda L, and thereby delta cos lambda L equals to 0, and this gives us that either delta equals to 0 or cos lambda L equals to 0. If delta is 0, then that there is no deformation of the member and there is no buckling, and if cos lambda L equals to 0, that gives then the what will be the value of lambda L, and lambda L in general will be equals to n pi by 2, from which if we substitute the minimum value of n, we get that critical load as equals to pi square E I by 4 L square. So, this is the critical load for a column member which is fixed at one end and free at the other. Now, let us look into the case where the column is fixed at one end and hinged at the other. Now, it is expected that the deformed state will be in this particular form, and if we try to find out the critical load corresponding to this state, this is P critical, and since this is hinged end, you have the horizontal force H. Now, if we take the free body diagram of this particular part, these are the moment, the horizontal force and the vertical force, the reactive forces here. If we take the moment with respect to A, we will have m plus p times y, y is the this distance, and since we are taking the section at a distance of x from the origin, let us call this as b, this is L minus x. So, minus h times L minus x equals to 0. So, this is the value of the bending moment m, and this if we substitute here, we get E I d2y dx2 is equals to m is equals to minus p y plus h into L minus x, and this if we take on the other side and divide by E I, we have d2y dx2 plus lambda square y is equals to lambda square h by p times L minus x, where lambda square you keep in mind as equals to p divided by E I. Now, to write here lambda square, we have multiplied with p and divided by p. Now, if we write down the solution for this, as you have seen in the previous two cases, the solution of this will be equals to the complementary solution and the particular solution, and complementary solution is C1 sin lambda x plus C2 cos lambda x, and the particular solution is h by p to L minus x. Now, the boundary conditions are that at x equal to 0, y equals to 0 will lead to C2 equals to minus h L by p. At x equals to 0, dy dx equals to 0, because it is a fixed end, that gives us the value of C1 as equals to h by p lambda, and this if we substitute the value of C1 and C2, we get the expression for y as this. Also, if you look into in this, that at x equal to L, this is fixed end and this is hinged end. So, you have a deformation in this. So, at x equal to L, you will have to satisfy that y is equals to 0. So, if you do that, if you substitute that at x equal to L, y equals to 0, from this expression we get this form, that tan lambda L is equals to lambda L. X equal to L means this term goes up, you have cos lambda L, this is sin lambda L, and this is equals to 0. So, that gives us a value of tan lambda L equals to lambda L. Now, this particular equation is solved by trial, and we get a value of lambda L equals to 4.4934, and thereby this is when you square this up, lambda square L square is equals to this square, which is equals to twice pi square, and so the minimum value of the load P will be equals to 2 pi square E I over L square. So, when a member column member is fixed at one end and hinged at the other, the critical load is 2 pi square E I over L square. Now, let us look into the case where we have a member which is fixed at both ends, and what will be the critical load corresponding to that. Now, again if we take a free body of this particular member at a distance of x, then the forces are like this. You have the bending moment, you have the resistive force, reactive force, and at this support you have the moment m. Now, if we take the moment of all the forces with respect to A, then we have m1 minus m plus p times y equals to 0. So, m1 therefore is equals to m minus py, where m is the support moment of this particular column. Now, Ei d2y dx2 equals to moment which is equals to m minus py is substituted here, and thereby we get, again taking py on the other side, we have d2y dx2 plus lambda square y is equals to lambda square times m by p, and again it will have the solution, the complementary solution and the particular solution, and thereby the y is equals to C1 sin lambda x plus C2 cos lambda x, and this is the complementary solution, and m by p is the particular solution as we have seen in the previous example. So, this is the expression for y, where C1 and C2 are the unknown constants, are to be evaluated from the boundary conditions. Now, what are the boundary conditions you have here? The boundary conditions are that at x equals to 0, y is 0, and that gives us that C2 is equals to minus m by p, and at x equals to 0, since it is fixed, it is dy dx equals to 0, that gives us a value of C1 as equals to 0, and thereby we have y is equals to m by p into 1 minus cos lambda x. This is the expression for the elastic curve, which is y equals to m by p into 1 minus cos lambda x. Also, you will have to satisfy that since the member is fixed at both ends, so at the top end where x is equals to L, there both y is equals to 0 and dy dx equals to 0. Now, at x equals to L, y equals to 0 gives us that cos lambda L is equals to 1, and at x equals to L, if we take dy dx equals to 0, that gives us sin lambda L equals to 0. So, we will have to satisfy both the criteria, that cos lambda L should be equals to 1 and sin lambda L should be equals to 0. Now, this can be satisfied only if lambda L is equals to 2 pi or multiple of 2 pi. Now, so the minimum value corresponding to this will be 2 pi, and if we square it up, we will have lambda square is equals to 4 pi square by L square, and since lambda square is equals to p by E I, so p is equals to 4 pi square E I over L square, and thereby the critical load corresponding to the minimum value, which is 2 pi, is equals to 4 pi square E I over L square. So, you see that we could evaluate the critical load for different members, or for the column members with different support conditions. First, we had evaluated corresponding to the both the ends hinged. Subsequently, we have seen that if one end is fixed, other end is free. Subsequently, we have seen that one end is fixed, other end is hinged, and now that we have seen that both the ends are fixed. So, in such cases what are the values of the critical load? And as we have seen that in all the cases the values of the critical load as we have obtained, they are the function of the member properties like the I and L, and you have the material property which is E, and the L is having some coefficient factor which we can evaluate now. Now, if you look into in general for these cases, now you see for the hinged we had P critical is equals to pi square E I over L square, where the deformed state was in this particular form. Now, if we try to write down the critical load for all the cases in terms of this pi square E I over L square, corresponding to this case where your support conditions are fixed and free, you have P critical is equals to pi square E I by 4 L square. Now, let me call that P critical is equals to pi square E I over L E square. Let me call this L E as length equivalent. So, when it is L square, L E is equals to L. When it is 4 L square, L E is basically twice L. So, here that is what is indicated over here. Now, in this particular case it is pi square E I over L by root 2 square, and 1 by root 2 is 0.7. So, thereby equivalent length here is 0.7 L, and in this particular case as you can see that this is pi square E I by L by 2 square. So, L E is equals to 0.5 L. So, these are the 4 cases as we have determined, and corresponding the effective lengths are as given by this particular particular row. Well, we have an example for you, which is a rectangular column 3 meter long, which is hinged at both ends, carries a load of 300 kilonewton. You will have to determine whether a section of 200 millimeter into 150 millimeter, which is a rectangular one, will be able to carry this load if we introduce a factor of safety of 3, and the value of E is given as 12.5 GPa. Now, this problem is assigned to you, look into this, we will discuss in the next lesson. Hence, to summarize, in this particular lesson we have looked into some aspects of the previous lesson. Also, we have introduced the concept of the buckling and stability of different types of column members. We have derived the critical buckling load for different types of columns. Different types of columns in the sense we have taken the columns with different end conditions, either they are hinged or you have fixed and free, or you have the fixed and hinged, or you have fixed at both ends. So, these are the possible cases that we can have, and corresponding to this we have derived the critical buckling load. And well, we have given one example, and some more examples we will be discussing in the subsequent lesson. And these are the questions set for you, that what is meant by critical buckling load of columns, how will you evaluate the critical compressive stress in a column member, and what is meant by slenderness ratio. Look into these questions. Some of the questions you will be in a position to answer from the lessons we have discussed, and we are going to give you the answer for this in the next lesson. Thank you. Welcome to the second lesson of the 9th module, which is on stability of columns part 2. In fact, in the last lesson we have introduced the concept of the buckling in a member, a vertical member which is subjected to a compressive force, which we have termed as column, and also we have looked into the stability aspects of different types of column members. We introduced the which was proposed by Leonhard Euler, which we normally call as Euler's buckling load formula. Now, in this particular lesson we are going to look into the aspects that where the Euler's load can be applied, or in other words what are the limitations of Euler's critical buckling load.